Okay, so so far it's fine. So we have constructed this. Now what is the next thing that we are supposed to do? We have to take an element E so that GCD of E and phi n is 1. So that was the next question that we have. So how do we take an element E so that E and phi n are lately prime? For that, what we can actually do is either we can take one prime between E and phi n. Okay, that's one possibility. So we want just a number in such a way that E and phi n are lately prime. For that, what we can do is we can take a prime between E and phi n. Okay, that's good enough, because if we take a prime between E and phi n, what happens is that, okay, that's not actually enough, because it can happen that this prime is going to divide phi n. So instead of that, suppose that we take a prime after phi n, and suppose that we take a prime after phi n, suppose that we take a prime after E. Oh, but E we don't know, right? Take an integer E so that E and phi n are lately prime. So let us do like this. Suppose that we have already found this phi of n to be 303576. Now suppose that we take a prime above phi of n, then definitely that prime is not going to divide, definitely that prime is going to be lately prime to this phi of n. So that we can choose as E. Okay, my idea is probably clear to you. So my plan is to take a prime greater than phi of n, so that it will be definitely lately prime to phi of n. If I choose a prime below phi of n, what will happen is that's not going to be probably lately prime to phi of n. Okay, choose a prime above phi of n. So maybe one of you can think about some other intelligent way to choose a number which is lately prime to phi of n. That's of course possible, but I'm not going to do that for so that we can quickly finish this part. Just take some prime above phi of n. That's it. And how is this guaranteed? I told yesterday itself that using Bertrand's postulate, there is a prime in phi of n, n to n range. Okay, we are simply going to use that. So take prime range from phi of n, phi of n 2 times. Maybe to make sure that if phi of n itself is a prime, we don't know. To make sure that we are not choosing this, let us take 2 times this. So this is going to be definitely more than that. And from this range of primes, choose the first element. Let us see what is this.
So can we take phi n plus 1 E equals to?
Certainly. You want
phi n.
Yes. Thank you. That's actually a wonderful idea. I actually forgot about that thing, that if you take one number and in fact phi n minus 1 also we can choose, right?
Yes.
Yeah, that's right. I have made a foolish attempt to make it much more complex, that taking prime after that it's not at all necessary. Thank you. Bertrand's postulate we don't have to actually use. Phi n plus 1 is good enough, but if we use phi n plus 1, but what are the things that we are going to announce as public key? N and D, right? Okay, N and D is the public key that we are going to announce to everyone. So suppose that someone guesses that we are using phi of n and phi of n plus 1, then is that knowledge going to be good enough to find n? No, that's not enough, right? Because for many numbers the same phi of n can be there for many n's. Okay, that will actually give a hint, but that doesn't matter because we are not actually implementing that in the actual practice. We are just trying to understand the problem. Therefore, what is said is more than enough for us. Choose E lately prime to phi of n. Choose phi of n plus 1 itself. You will choose phi of n plus 1. Good, thank you. So E is taken to be phi of n plus 1. Okay. Sorry. Euler phi. That's okay. So 303577. So we have two numbers. Okay, so we got two numbers. Therefore, now what do you want? Now we have constructed the public key is now ready because we have n, we have e. Public key is n, e. That's ready. We may announce that this is the public key. Now the private key we have to construct. So for constructing the private key, what we need is we have to solve d such that d is equal to 1 mod 5. Okay, so we need to solve. So let us solve. Solve mode. D equal to solve mode. E star x equal to 1. Equal to 1 is what we are supposed to solve, but that is modulo E star x equal to 1, and that is mod what we are supposed to solve, mod 5. I think we have to enclose this in square bracket. Oh, sorry, once again. Oh, this is so enough. But now see that D is the solution is appearing as a list of tuples. So to extract this, take 0 and 0. Okay, are we supposed to solve this? DE congruent to 1 mod 5. Okay, I think that's correct. So somehow we are getting a very small d. I think that's that should not create any trouble, but I guess so. P, Q, and D. Okay. Anyway, whatever. So solve for some d such that d is equal to 1 mod 5. Now, if you want to take a large d, what you can do is you can just take that plus 5n. That plus 5n also we can use if you want a large number. But that doesn't matter. Whatever 5 we are going to use, all these 5s are going to serve the same purpose. This is anyway private key. That's it. So the private key is PQD. So both these things are ready. Now the encryption is going on. So for encryption, what we need essentially is, so we need to take a message which is less than n. Therefore, the message has to be a number first of all. So how do we convert a text message into number is the first thing that we want to see. Okay, suppose that our message text. Suppose we call it like this. Message text is hello. Suppose we take this. Okay, so for that what we are going to do is we are trying to see that we are going to map this HELLAO to something called ASCII table or Unicode, whatever it is. I don't exactly know what we are going to call this. So we are going to use the function called ORD for that. Okay, so ORD, for example, ORD of H, where H is the character. ORD of H is nothing but it's 72. Okay, ORD of small h if you choose, it's 104, right? So ORD of, we have chosen ORD of H, therefore for all these characters and message text, we are converting that into a list. Message number, or let us call that to be M for typing simplicity. Now what we are going to do is we are going to apply the ORD function, ORD C for C in message text, and let us see what this is. That's it. This is still not a number, but instead of that, this is 7269767679. Okay, now how do we create a full number from this? So for creating a full number from this, what we can do is we can multiply this 79 with 100. Take 79 as it is, multiply 76 with 100, multiply 76 with the 100 square, multiply 69 with 100 cube, multiply 72 with 100 to the power 4. So essentially what we are going to do is for I in range length of m, okay, we are going to multiply each and every number with m number equal to 0. We are going to multiply each and every number in this m with what you call 100 powers, and then we are going to add. So what will happen after that? Let us see. So how many times we have to add? We have to start from the right side. Okay. So if you have to start from the right side, okay, if you start from the left side, what will happen? Left side will be 0th element 2. Okay, we can start with 0th element also, but in that case, with what we have to multiply? 0, 1, 2, 3, 4. 100 to the power length. M number plus equal to m I, m star, initially I is 0. So I is 0 means we have to multiply with 100 to the power I. I hope that this is correct. Okay, let us see. Seven nine. So what I did here, 79 I multiplied with 100, not 79, sorry, 72 I multiplied with 100, 69 I multiplied with 76, 69 I multiplied with 100, 72 multiplied with what? This is the first element, so 100 to the power 0, just 1, that's why it's coming here. 69 I multiplied with 100, that's why it's coming like this. So I would have actually reversed this order, right? I would have actually reversed this order instead. Okay, let us keep in our mind that this is actually this has actually got reversed. Okay, the numbers are now appearing in the reverse order. Now we can retrieve this entire list from this 72, 69, 76, 76, 79. It has become a number. I hope that you agree with all these things, whatever we have done so far. We just converted m into a number. So we are doing this basically because we cannot concatenate a set of numbers. We can concatenate a set of characters. Otherwise, we need to convert this into character and then we need to concatenate. That also actually can be done. But then there is still another problem. I will try to explain that problem later. So this is the conversion is now done. So m number is now ready. So what is the encrypted message? Now for encryption, remember that m has to be less than n. Is this m less than n is the first thing that we have to check. What is our n? Where is the n? M is 30. What's the private? What's the public key? N equal to PQ. Public key is NE. 304679 is the number that we are getting, but we need to take something more than that. So because our message is somewhat large, message is a large number, we want that to be, therefore we should choose larger primes. So let us take 200 and 201 and see. That's also not enough. Let's take 1000, 1001. Otherwise, let us reduce this. High. Okay, that's good enough. We just change the message. Of course, we can take a larger prime, but instead of, I am actually afraid that if you take a larger number, then again the system may hang or not. I don't know. Therefore, I'm stopping with this prime. This is good enough for us for testing. So the message as number is here. Message as number is here. So what is the next step? Once you have found this m, what you have to do is we have to take c congruent to m to the power e mod n. This is what we want. The encrypted message is here. C what we are supposed to do, power mod. Power and mod we have to give. Power is here, this is here. Encrypted message is nothing but C. Oh, sorry, I should have taken M number.
No, there will be no star, I think.
Sorry?
Yes, M number star power mod 12.
Where is that?
C equals to second last line.
M number dot.
It will be dot.
Yes, it's a dot.
Okay.
That is correct. Essentially, the problem is that if you are taking m number to the power e, what is e? E we have chosen to be just equal to 1, right? I think e is 1. Am I correct? PQ, no, e is not 1. PQD is 1. Is it because of that? Okay, let us choose d to be something. Maybe we can take even, can slightly modify this d, but even if we modify d, nothing is going to actually happen. I don't really think that. No, that is not going to make it, because anyway the modulus is going to be the same. Why we are getting exactly the same number? What is m number? This is power mod e, m number to the power e. What is e? E we are choosing to be e. Oil of phi n. Okay, what is the condition on E? E and phi n must be 1. Take integer E, so that this must be true. Okay, but suppose instead of this, suppose that we choose, where is the C? Where is the construction of E? E is here. Okay.
30.
Sorry?
303577.
What is that?
303577.
That's E, right?
E, public key. In public key we have N and E.
What is there any other condition on E? E is the only condition is that GCD and GCD of E and phi n must be equal to 1, right?
Yes.
So N and E. No, what I'm wondering is why we are getting exactly the same number 7372. Because there is no encryption at all happening. M number, power mode, En. Exactly the same number we are getting here. Okay, right. Let us try to change this. What we did initially. Let us try to change this e to something else. Oh, but where did we calculate? Okay, this I have suppressed. So let me just take e as I told. Let me just take e to be something in the range. I'm just trying. I'm not very sure whether that's going to work or not. Euler phi n plus 1 to 2 times that number, and the first number among that. If I choose it to be this, I am somehow okay. That we can probably try to see what exactly is happening. Anyway, if you choose e to be something larger than this, it's definitely it seems to work. It seems to work in the sense that it's encrypting. So I chose e to be a prime in the range Euler phi n plus 1 and 2 times Euler phi n plus 1. That's the first prime in that range. So if I choose that, I will be definitely getting some number which is relatively prime to Euler phi n. That's what the logic is. Of course, this Euler phi n plus 1 should have given exactly the same kind of effect by giving a prime within this range, but somehow it's I'm not getting that. Okay. Anyway, let us try to see what exactly is the problem. We will try to see later. But anyway, if we choose e to be a prime in the range prime above Euler phi n plus 1, it seems to encrypt at least. So the encrypted message is here. So we have encrypted the message. Now, how do we decrypt? That's the next question. How do we decrypt? For decryption, what we are supposed to do? We are supposed to take m equal to c to the power d mod n. Okay. So decrypted equal to c to the power d mod n. Which one we are supposed to take? C. C power mode. What is it that we used here previously? Power mode. D mod n. Encrypted message number. Similarly, decrypted message number is nothing but DCR. Okay, let us see what this is. So we got 7372. We got 7372 was the previous number. Now we got 7372 once again. Okay, we got exactly the same number. Now, how do we convert this into again back to back to the message itself? So for that, what we can do is from the end, let us suppose we divide each and every, we divide with okay, what we will do is, suppose that we divide this number. Suppose m is an empty list, so to m we are going to append. So 7372, suppose that we divide it with 100 and take the floor of that, or 7372. Okay, we know the so 7372. How do we know that it's going to be? It's a multiple of 1000. How do we understand? So 7372 is the number. We need to extract 73 and 72 from that. But how do we do that? Okay, let us divide that number with 100 first and take the floor. Percentage 100. So what is m? M is now 72. So what is the order of the numbers previously? (72) and 73. Now we need to again append. But before that, let us divide equal to floor of by 100. So how much we will get? We will get 73 point something. After that, again the same thing. So we got 72 and 73. What was the original message? 72 and 73. Now let us convert this back to characters. For C in M, HI, and now join. Okay, join with an empty string. So how do we convert this as a single string? So we may take an empty string in the sense that no content, and join to that.
Sir, if we multiply 73 by 1 and 72 by 100.
Yes, that is also 73 by what?
By 1.
For what we are doing all these things?
Means for concatenation.
That is what we have previously also done. We have already done that, right?
Yes.
So 100 to the power. That's exactly the same thing we did. And we added. No, what I am now checking is S join M. Why this is not S is equal to. Are we getting something? Yes. So I set S to be an empty string. To S I joined this M. Or can I just take this? No. I need to join this to something. That's it. That's high. If you choose a large prime, what will happen? That's another question we have to ask. 200 or 500, 400. Then also will work. Test. Okay, there is a small problem if I use a lowercase letter, because lowercase letter I need to multiply with 1000 in that case, because lowercase letter the ASCII codes are more than what you call 100. Test. Here I need to be really careful, because previously I know that there are only 2. Here for that what you have to do is I need to do it in a loop, otherwise I will not succeed. While greater than 100, is this going to work? Z is it. What's the problem here? Forty, 90, 90. What is the decrypted message number encrypted? Is correct. Public key is this. 5 of n is this. Private key is P, Q, N. So message number 8486 etc. 98. So what is the condition that we require? M must be less than n, right? M must be less than n. Is the condition satisfied? M, what is M? Oh, I think M is larger than. That's why we are not getting it correctly. Decrypted message number. Messages number is 83 this, and n is nothing but n is this. So we need something larger, still larger. 1000. I think it mainly depends on TES. Why is it giving 4 characters? There is something wrong here. We have only 3 characters, right? Decrypted message number is 836984. 8369. Okay, the mistake is happening here. 8469 But why is it happening again and again? It's equal to floor. Okay, I should not have. So initially what happens, so the number is 836984. From that we want to get 83,69,84. So initially what happens is, this is divided with this split with percentage 100. If we take, we will get 84 as the first one. So divide again. So DCR by 100 means 8369.84. So that is just 8369. Now 8369 again divide with, oh, this is not necessary. Okay, that's a mistake. This is not actually required because it's a loop. Okay, what's happening to this? Yes, then we are not supposed to do it here, but here. Or otherwise we need to do it twice. The last one we need to separately append. TST. Okay, then we have to choose. Yes, because the primes we require large primes if the message is also large, because we always need the m to be less than n. So if we choose a large text, it essentially means that the number to which we are converting that text, that's also going to become large. So if it becomes a large number, the message is large, the text also, the equivalent number also will be large. Therefore, the prime we are choosing also must be large so that m is less than n. That's one problem here. Okay, it's not actually a problem. So usually we take much large primes, so whatever sufficient size message will pass through that encryption technique. So let me just update the Google Sheet with all these things. So far done.
So this RX algorithm, where has it implemented? Is it implemented in our browsing, that Chrome or Internet Explorer?
I think yes. So Internet Explorer, what happens is that the public key, private key. That's what I tried to explain yesterday. So who is storing this public key and who is storing the private key is one question, because we are not doing any of these things, right?
Right.
We are not creating any public key, we are not distributing any private key, we are not distributing any public key, we are not keeping any private key. But what happens is, there is something called browser with us. So the Google server is handing over one public key to Firefox. Okay, so Firefox encrypts whatever password we are typing. Firefox transacts, or Chrome, whatever, transacts this password to Google server. Google server knows the private key, right? So it encrypts the password. So is that logic fine? It decrypts the password, sorry, not encrypts, decrypts. So what happens is, so that's first step. In the browser, this second step. And sends to Google. And finally what happens is, so this is actually happening between, this kind of process is actually happening between every site which has HTTPS in the browser address bar, HTTP secure. So what happens is, every server which has this HTTP server, it actually sends a public key to the browser. Browser encrypts it, and the encrypted message is now sent to the server. The server decrypts it. Okay, so this is how we implement the RSA using SageMath. Of course, so what are the Sage features that we have used here? We need to just carefully analyze. These are all Python features. The Sage features we used are the power mode we used, and solve mode we used, prime range we used, OILFI function we used. These are the Sage related commands that we used. Using this entire set of commands, we can encrypt any message, provided that we know the public key of a person to whom we want to send this message. Once we encrypt that, we are sending it to that person. But anyone, whoever is capable of eavesdropping, that means that overhearing the message, will not be able to decrypt it unless he has access to this private key. But private key is only with us. So therefore, our message is assumed to be safe until it reaches the server or the person to whom it's actually intended. That's the logic. I have already updated the Google Sheet. Let me just add the last few lines as well. So done. So I have already shared the Google document link. You can have a look. Okay, so that completes the RSA part, and of course you can do several other problems with the help of SageMath, but once you understand the basic commands and the way in which we are doing things, probably you can try to do many more problems in your own. So let us just focus to something, some simpler things in complex analysis now as per the workshop schedule. So we are going into complex arithmetic now. A complex number in Sage is denoted by a plus b star I instead of a plus bi, or so the small I as well as capital I will work, but Sage will always denote in its internal commands by capital I. So if you ask type I, remember that we have not used this I symbol anywhere. If you use the I symbol anywhere, then you may not be able to access this I. So this is int, but why is this int? Why is it giving us int? I think previously we have used this I as int, so that's actually a problem. So let us use capital I instead. This is a symbolic expression, and I square, if you try, you will get this to be equal to minus 1. Three star I. You should use 3 star I, not just 3i. Again, a symbolic expression. And suppose we write, or we put it's equal to this, then we can extract the real part and complex part of a number like this. Now it's possible to find the conjugate as well. Conjugate, it says that the representation is minus 3i plus 2, but of course if you use the show command, probably you will get still minus 3a plus 2. That's the internal representation, it seems. So if you use the just z, okay, z is also represented as 3 star I plus 2. Therefore, even though the representation we are trying to give is a plus bi, Sage is returning it as bi plus a as the expression. And it can perform additional multiplication, etc., all in the usual way. 1 by 5 plus I. Inverse. And we can take, of course, the in the usual, the otherwise also, instead of using this symbol, we can just take minus also, like this. This is also bad. And this actually can take this form, real sometimes there are two forms for doing the same thing in SageMath, like this. Now we can find the argument also. Remember that we can find the argument by taking suppose that we have a plus bi as the number, then we can find the argument in some other way, right? So because if we take x plus iy to be this number, then we need to represent it as r cos theta, where r is the modulus of that. Then after that we have to solve for cos theta equal to, so after removing this r, after making the modulus of that number to be 1, after removing r, then we take cos theta is equal to this and sin theta is equal to this, and we have to take the inverse, we have to solve this system of equations that cos theta is equal to some number and sin theta is equal to some other number. But instead of that, what we can directly do is we can take argument. So let us choose z to be equal to 5 plus 2y. So argument z. This is tan inverse 2 by 5 is what it says. Tan inverse 2 by 5. Let me update the Google document with the comments so far. So these are the basic things in basic operations in complex analysis. Now we can convert. We can actually find out the we can find out the polar coordinates of the what you call modulus amplitude form of a complex number. We can actually define a function. That's quite easy. So for that, what you have to do is we have to take the argument. We have to find the modulus. These two things we have to find. For example, something like this. Z we have already taken. R equal to absolute value of Z. So R is now formed. So what you next need is the argument. So that's it. So for modulus amplitude, we will be getting R So if you want a numerical expression, probably we can try with this as well. So 5 point something is the modulus and 0.38. This is in radians, remember that this is the moduli. Sorry, this is the amplitude. And we can solve as well. So solve command also will work. Even on the complex polynomials, the solve command will work. Let us take f to be equal to f equal to 2x square plus 3i. If we take x to be this, and suppose that we want to solve for this, showing f, 2x square plus 3i. So if you solve, f equal to 0, 4x. You are getting the numbers to be this, or even if you use show, that is somewhat a strange output, but maybe what we can try to do is, okay, let us call this to be roots, f roots, and let us take the RHS. Okay, f roots dot RHS, f root 0 RHS, and f root 1 RHS. Okay, show is not required. We may try to actually simplify this, because this seems to be somewhat, no, even that's not working. Or maybe even we can try with approximation. Okay, the approximation is anyway working fine. So complex polynomials also can be solved. That's the only thing I wanted to say. I'm updating. So next thing is we can check whether a polynomial is a complex polynomial. A complex polynomial in the sense that, so if we have a polynomial in terms of z, that's going to become analytic. But suppose now that a polynomial is given in terms of x and y and has complex coefficients. So for checking p of xy to be, if it's a complex polynomial, if it's analytic or not, there are actually two ways. The one method is to check if p of xy and p of xy is actually equal to p of z0 or not. Okay, that's one method. P of xy. So what we essentially do is, equal to z0 or not, where z is equal to x plus iy. For example, suppose that we take p of x, y, maybe we had defined var x, y, p of x, y, suppose that we define it to be x square plus y square minus 2i x y. And suppose now that z is equal to x plus I star y. So what are we supposed to do now? We are supposed to check p z0. So show p, substitute x equal to z, y equal to 0. Just this is also, I think, good enough. This is what p of z0 is. Now let us see if this p of z0 is the same as the other expression or not. Equal to p. That's not the correct answer that we are looking at. Maybe we can even expand and see. So here the expansion, x is equal to z and y is equal to 0. That shows that p of xy and p of z0 are exactly the same. Oh, but they are not the same, right? You would have taken, here it is x square plus y square minus 2ixy. But here it is the other way. So maybe if I use this minus here, even then, okay, that's not going to be correct. We are not getting there to be equal, therefore they are not, this is not analytic. So on the other hand, now suppose that instead of this, suppose now that we check something else. So x plus iy square itself. So x plus iy square is nothing but x square minus y square plus 2ixy. Yes, this one seems to be analytic. Okay, that's one way. So I have updated the Google document with this. Now the next method is to actually use the Cauchy-Riemann equations, which essentially says that if you have, you can say that if the partial derivatives exist and if they are continuous, then we can say that the function is analytic. So we can check the partial derivatives first of all. So the same two polynomials we will try. First one first. So what do we do? First partial px equal to p with respect to x. Oh, sorry. I should have taken it the other way. That's not the correct thing, because we need to take the real part and imaginary part instead. Sorry. So let us see if we can take the real part and imaginary part like this. U is equal to P. I don't know whether the real imaginary will work on symbolic things. I'm just trying. What is this U? That's x square plus y square. Yes, it is giving something sensible. So P dot real and V equal to P dot imaginary, and therefore it gives some complex expression otherwise. So U and V are here, minus 2ixy. Now what do we need to check? Ux and Vy. Ux equal to differentiate U with respect to x, and Vy equal to differentiate V with respect to y. V with respect to y, and print both. Maybe we need to simplify these two. No, we are not getting that, at least here. So can we ask if they are equal or not? Ux equal to Vy. Else Ux not equal to Vy is what's printed. Now same way we can find Uy and minus Vx as well. Let us use the other example. This is not necessary. Ux equal to Vy. So the function is therefore analytic. But of course we have to check the continuity, which we have to do manually, because the continuity, there is no function. Instead of that, what you can try to do is just see okay, we need to actually specify at which point the continuity is we want to check, because otherwise the function is not capable, the Sage is not capable of checking the continuity in a range. It can check the continuity at some specific point if you use the limit, left, right limits, and the evaluation at that particular point. So this we cannot definitely say. We need to check the continuity also. So that's it. Checking analyticity using CR equations. So I have updated the Google document. So while telling things about complex polynomials, I think there are a few things that we need to actually explain about polynomials itself. Okay, we haven't discussed anything about polynomials, but I need to say a few things about polynomials before going further. So for polynomials, the basic thing is that you can define polynomials. We have already seen how to define polynomials and how to evaluate them. Evaluation is actually done through substitution, and after that we have a few commands like expand, full simplify, etc. But these things are necessary because sometimes what happens is that if you multiply two polynomials, Sage will simply show it as that product itself. Okay, for example, suppose that we multiply. Suppose that we define f equal to 2x plus 3 and g equal to x plus 5. So we don't know what this f star g is going to be. F star g is simply shown like this. This is not actually what we expected. We expected that to expand it completely. So to get that expansion, what we need is we can probably try to expand it. And even show. Now suppose that on the other hand, we do the opposite thing. If is equal to 2x square minus 3, and suppose now we ask for two star. So it's not giving anything. There is actually one problem, small problem, that Sage tries to factor certain things based on the field in which we are actually standing. If you do not declare any fields, what happens is that looking at the coefficients, it tries to understand one field, and only in that particular field it tries to solve. Okay, that's one problem. Okay, for that we can actually specify that if a variable which we are going to define is actually what you call a monomial, or a variable in one particular ring that we can, in particular polynomial ring, we can define. So the definition is actually something like this. We may simply give one name like this, ring of polynomial. Suppose that we call that with the name RP. Suppose we use the symbol T instead of using X and Y, which we have already used several times, and polynomial ring over QQ. So if you do this, then now if you try to factor, the factorization is just this. Okay, even previously, if we didn't even get this. Now suppose that we use this instead of Z. So the factorization is simply this. So now you can probably guess that why the 2x square minus 3 polynomial got factorization as 2x square minus 3 itself, because the coefficients were from the set of whole integers, therefore it assumed it to be a polynomial ring over Z. That's why we got a reply like this. But instead of that, here we changed it to QQ. Okay, let us modify this example, keep on modifying this example. Polynomial ring over QQ. See that the answer is changing, keeping on changing. Show. What's again? So 2 square minus 3 over R, we are getting it to be this. This is over R. Now, if you use, okay, now suppose that we use instead of 2 square plus 3, there is no factorization because still t square is appearing. Now suppose we use 2 square plus 3 and use the ring as complex ring, then we get a factorization. See that all these things are happening because all these things Sage determines based on the ring over which we are defining the polynomial. So if you define a polynomial to be in one particular ring, the factorization will happen only in that ring. Factoring let me update the Google document with this. So that so we can in fact define multivariate ring also just like this. So suppose that we want to define multivariate polynomial rings. So I think we can simply use U and T over Q. Suppose we write T square minus U square. Suppose we try to factorize it. This is also possible. Now, is it possible to find the quotient, remainder, etc. using, can we divide polynomials? That's another thing that we want to ask. Can we try to divide polynomials and see the quotient and remainder? And can we find GCD of two polynomials? Let us fix the polynomial ring to be again the rational field. A ring of polynomials with variable x to be polynomial ring over Q. Suppose we take 2x square plus 3 and G equal to 5 x plus 9. So if we take this, then what we get is, let us try to see what this f by g is. And expand, simplify something. That doesn't seem to work. Let me update this multivariate thing. Have I done that in the Google document? No. So this is not working. So for dividing polynomials, the only way is to use something called, so if you want to divide a polynomial and you want to produce quotient and remainder, so we have to, there is no direct built-in command available in SageMath, but instead of that we can use something called the help of a software called Maxima that's available in SageMath. But unfortunately there is no direct command that could be used in SageMath, but instead of that we have to use the Maxima command. So the command is something like this. Maxima methods is the library used for creating quotient and remainder when we try to divide a polynomial with other. So same thing. Now print, okay, or okay, correct. We are trying to divide f with g using a method or technique available in Maxima, the software Maxima, which is available in SageMath. Divide. Oh, this is f by g or g by f, I don't exactly know. Let us see. What mistake we have done? Print f maximum methods divide g. F divided by g. What does it say? Sage has no attribute. Okay, why is it like that? R is equal to, or let me just see. Okay, let me search for why is exactly this error is coming. directly we can find, of course, I don't know, I'm just trying with another command, which is this doesn't seem to actually work. So quotient remainder, will it work? I don't know. If dot quotient okay, this seems to work. Instead of going into maxima remainder, is this correct? So what is the show output? So 2x 2 by 5 x minus 18 by 25, this is the quotient, and 237. So essentially this is a tuple. So let us just do quotient and remainder. Quotient remainder to be this. Suppose we take it to be this and print quotient comma remainder. So we are getting both of these things like this. So this way it can actually be, I don't know, let us just try to see once again and try to add these two and see if this is actually correct. So qt star g, okay, qt star g. So what we are supposed to get, qt star g plus remainder must be equal to f plus 2x square plus 3. That's correct. So we can extract, we can find the quotient and remainder like this. Okay, that's correct. So we can find the quotient and remainder like this, and of course we can then say that if g is a factor of f0, we can say from this, if r equal to 0, g is a factor of f. Else not a factor of f. Now the GCD also can be found exactly in the same way. GCD of these two polynomials f comma g. For that, GCD command itself is enough, I think. Let's see that. There are no common, because already we have seen that it's not a factor. 5 star x 9 plus 9 is not a factor, but okay, it doesn't divide also. This is not. Doesn't divide also. Now one more, okay, let me update the Google document with this. if you want to get the list of all coefficients, suppose that we want to extract the list of coefficients, suppose that we want to see there are a few other commands associated with the polynomials. Some of the commands are that suppose that we want to see the degree of a polynomial for some reason. Okay, degree of a polynomial for some reason, if you want to see, let's take f to be equal to 2x cube plus 5x square plus 6x plus 2 or 3. So degree can be obtained using directly degree of f. Or f dot degree. Sometimes this degree of works and sometimes that doesn't. On the other hand, suppose that we have a ratio of polynomials with us after the result of some computation, and if you want to extract the denominator, or if you want to see the places where the denominator is becoming 0, that sometimes that may be required, we can use the denominator command. G we take to be again this. Suppose we consider 2x square or 3x cube, 6, 3. So everything is a factor of 3. Suppose we take G equal to 3x plus 2. Now we know that f by g is this. See that this has actually got reduced by taking all these 3 out. Now suppose we want to take the denominator of f by g. Is f by g x plus 2 by 3. And what are the points of discontinuity? We can simply equate the denominator to be 0. Not actually points of discontinuity, point that function does not exist. Existed, solved, this is equal to 0 for x. Because we have defined it to be this, to be over this. So if we define it to be this, what happened is the solve is not working. Okay, solve f by g
Sir, can you write that denominator within the bracket x variable? I think it is taking some not a function.
Sorry?
That solve and their denominator, and within that yes, there within the first bracket, if we can write x, because the previously we also having this sort of problem, and after that when we give
So,
that
do you want to say that solve in bracket or what?
solve of denominator, and that within the after that denominator, the first bracket, and there is x. Okay, denominator, then that two brackets is there. After that, denominator are.
No.
Yes,
So, this is the syntax is correct. The only problem is that what the problem here happens is that x is not assumed to be an ordinary variable, but instead of that, x is supposed to be the generator of the polynomial ring QQ. Okay, it's a generator of the polynomial ring QQ. It's not compatible with the solve command. So previously we were using x as just a symbolic expression, but now it is not just an expression. It's actually the generator of this what do you call QQ, polynomial ring over QQ. That's a problem. Okay, let me just use an alternate method. We just try to use an alternate method. R is this, we have already defined the polynomial ring, and we have okay, let me just try to do something else which I am finding from the documentation. RP is defined with this. After that, I have already taken this, R equal to
Yes, sir, I checked and it is working fine. If you just write the denominator within the first bracket x variable.
I didn't understand. Denominator within what bracket?
Yeah, that's the last line.
This line?
Yes, there. After the after R, at the first bracket is there. So after R, that first bracket you have given, right?
Yes.
Within that, write down x variable.
Here itself.
Yes, and equals to 0. Oh, all right. Yes.
And one more x is required. Oh, that's not working.
But my system is working.
What is the meaning of that thing? What is
I'm getting one root is -1, another is 1/2, something like that.
But no. What is the meaning of that expression? Suppose that you are substituting. Suppose instead of x, you substitute t. Okay, let us just try it this way. I don't know whether this will succeed or not. Okay, suppose that I am defining another variable. I don't know whether I will succeed or not. I am just trying. Denominator subs x equal to t. So I substituted. So if denominator is here, denominator takes no keyword arguments. Okay, it doesn't take. That's okay. I will do one more thing. I will try to do one more thing here. So let me just take denominator is equal to this. Suppose print dn. Okay, that's at least that is working. Okay, at least that is working. Dn is working. Now let me just change instead of dn equal to dn subs x equal to t. I don't know whether this is in fact going to work or not. I am just trying. So this is t plus. Now this is dn is the denominator. Solve for dn equal to 0, say.
And t, and variable is the t.
Yes. Yes, that works. So essentially the problem, as I told, that now x here is taken as the generator of the polynomial ring. So 1 and x are the generators of the polynomial ring over Q. So therefore x is not considered to be a symbolic expression kind of thing. So instead of that, what I did is I just changed the symbolic. I just wanted to introduce a new variable, because it actually doesn't matter if you are solving it in terms of t or x. Therefore I simply introduced a variable t, and that variable t is substituted for x. So now we have an expression in terms of t, which is a symbolic variable, which solve command can handle. So dn is equal to 0. I solved in terms of t. That's what I did. This works. Okay. So for checking the existence of function at several points, we can probably use this. And from the documentation, I am finding another technique. So let me just try to explain that also. So instead of doing this, so instead of substitution and all these things, I am trying to do this. If at all this works. So let me define polynomial ring with we want define the polynomial ring as well as the variable. So let me just take another notation R. So X polynomial ring over QQ or just instead of even this QQ over X. Will this work? Solve is still not, therefore this is not actually a valid method, but okay, anyway, what we have tried above works. That's the only thing we can see. So this actually works. Changing that existing polynomial ring generated to some other variable name gives the correct answer. That's the only thing I see to work. Anyway. Okay, now that's it. We can we can find the denominator as I told. Now, if you want to get the list of all coefficients, suppose that we want to get the list of all coefficients of a polynomial. That means here we have taken x to be f to be equal to 3x cubed, 6x square, 6x, etc. Suppose that we want to get the coefficient of the largest power we have, coefficient of largest power of x. Suppose we take the coefficient, suppose we are defining like this, and we take the coefficients. So we can probably simply use this f and we get the coefficients like this. But we are not very sure that from where it's counting. So let us just take it to be 7. So it's the counting is starting from 3 onwards. Therefore, the highest power is the last one. Highest power is for the last one. Therefore, the coefficient of highest power, how do we locate this? So we need to take a degree. Degree is here 3, but that is not actually sufficient. So suppose that we have 0 here, what will happen to 0? Suppose that we take this to be equal to 0, this is absent. Okay, still he is giving it to be this. So when we are taking the list of f, it takes care of the coefficient, it takes care of the powers with 0 coefficients as well. So that's not a problem for us. Therefore, coefficient of highest power, if we ask for the coefficient of highest power, so if we list this f, so the first coefficient is actually the coefficient of the last one. Therefore, if we reverse, what will happen? So reverse, will it work? I am forgetting that command for reverse. What exactly is that? So reversing list, yes. Reverse method actually is there, but somehow, okay, reverse itself is the method, it seems. That's a Python thing. It's not actually a Sage thing. Okay, what is this type first of all? Is this a valid list? Yes, it is a list. Okay, let me do another thing. So let us take coefficients. Instead of doing like this, maybe this is not working because of this. I'm taking it as list. Now reverse it like this. So 5. What was it previously? Okay, now it's fine. In the decreasing order of powers, it's here. Therefore, the coefficient of highest power, we can simply take this as the 0th element. We can take it to be like this. Coefficient of highest power is, oh sorry, I didn't reverse. It's here. And now we have already seen factor, but there is a factor mode also, in the sense that if we are factorizing, suppose that we have a polynomial and suppose that we want to factorize a polynomial in terms of some prime, for example ZP. Suppose that we want to factorize x square plus 1 in ZP, x square plus 1 in ZP is actually x plus 1 into x plus 1 itself. Okay, let us try to see that. F of f is equal to x square plus 1, and suppose we factor mode. Suppose we factor this f mod 2, what happens is x plus 1 the whole square. So this is factorization in ZP. So this is essentially in ZP, the ring is ZP. Not necessarily the ring, I don't know whether the factorization will actually work in some non-primes. I'm not very sure about that. No, the factor mod P must be a prime. This is not working. Let me update this thing in the Google document, and this one also.
is it possible to multiply two polynomials?
We have already seen that. Just use that star notation. Star is a simple, directly we can
Yes.
multiply.
Oh,
And multiplication, division also we have seen. But division, what we have seen is that if it doesn't factor, there is actually, it will simply show it like that. If you want the quotient and remainder, you need to use this.
yes.
It will divide. If it's a perfect division, it will divide. For example, if you are dividing x square minus 1 by x plus 1, it should divide. So let us see that. F is equal to, or otherwise, print x plus 1 star x minus 1. It's doing. Simple star is enough. Now,
Yes.
if you want to factorize x square minus 1, now you need to be really careful because you need to define the polynomial ring. After that only you should try to do all these things. This is the problem because x square minus 1, that Sage is assuming that since you have not defined any polynomial ring, probably it's assuming that you are doing all these things over x square minus 1, what is the factorization, x plus 1 into x minus 1. So Sage will assume that you are trying to do it in ZZ. So if you try to do, I think we have already defined it here, x to be a variable, or maybe you can in fact, oh, here you have simply printed, I'm really sorry, you have not used the factor command here. So factor, if you use, it will factorize because x is already, we are already in the integer ring. So factorization is okay, and division also works. X minus 1. So this all these things are working. There is no problem.
Yes. Yes.
Now one more small thing is that okay, one final command I will try to explain. GCD we have, okay, GCD also can be actually found. GCD can be directly found. Like so we have seen already two polynomials here. Where is that f and g? Yeah, this is our f and g. So GCD f comma g so this is our, okay, sorry, not GCD, f dot GCD, that's the command that we have to use here, not the usual GCD command. GCD of f, somehow this is actually GCD of, did I use D there? GCD, that's it. So the feedback link is already here. Just copy and paste. So probably I think we have seen a little bit of complex analysis and some what do you call it, something like basic dealing with polynomials. And after going into abstract algebra, we will try to see a few more commands like irreducibility and such kinds of things which are closely related to Galois theory kind of thing, if the time permits, of course. So with this probably we will stop today's session, and if there are any questions related to the topics that we have discussed, you may please, I can try to answer and you may please ask. Thank you. So as I told, I think tomorrow's session, what we are supposed to discuss. Tomorrow we will be dealing with abstract algebra, in which we will try to define the congruence groups we have already seen. The finding out generators, generating unit groups, little bit of things we have already seen. Now permutations and finding roots of polynomials in various fields. That also we will try to see. Polynomials in various fields, not actually in just one field. And we will try to see how the permutation, how to see the permutation groups in action and all such things we will try to solve. Okay. So we will focus on the permutation groups probably tomorrow.
Thank you, sir.
Thank you, sir.
So thank you very much, and we will meet tomorrow at the same time, 6 p.m.